Hi guys, this is Viha Suhasbhat from SEC. My USN is 1B22IS059, and today we're going to talk about optimal binary search trees. So what are optimal binary search trees? It's also known as weighted binary search tree. It's a binary search tree that minimizes the expected search cost. An optimal binary search tree is a binary search tree for which the nodes are arranged on levels such that the tree is perfectly balanced, minimizing the average cost of searching for elements. This concept plays a crucial role in optimizing search algorithms and data retrieval processes, especially in computer science and information technology. By strategically organizing the nodes in a binary search tree, the search process becomes more efficient, leading to improved performance and reduced time complexity. Understanding the principles of optimal binary search trees is essential for developing efficient algorithms and data structures. So, what are binary search trees? A binary search tree is a data structure that allows for efficient search, insertion, and deletion of elements. It is composed of nodes where each node has a key and two distinct children, a left and right child. The key is a node. The key in a node is greater than all keys in its left subtree and less than all the keys in its right subtree. The hierarchy organization enables quick search operations, making it a valuable tool in computer science and programming. Binary search trees are used in various applications such as database systems, priority queues, and even in optimizing algorithms. They provide a way to store and manage data that allows for fast and easy retrieval, ensuring that the data is organized in a manner that facilitates efficient searches. Understanding the principles and characteristics of binary search tree is fundamental for any programmer or computer scientist. So, why are binary search trees important? Firstly, they give efficient search operations. Secondly, optimal storage utilization. They have enhanced performance, and statistical analysis and data representation gets easier with optimal binary search tree. In the picture, you can see a few examples of binary search tree: the perfect binary search tree, complete binary search tree, and balanced tree, and an unbalanced tree. Efficient search operations. So optimal binary search trees are important because they enable efficient search operations. By placing frequently accessed keys at the root and keeping keys with similar properties together, these trees minimize the average search time, making them crucial for applications requiring fast retrieval of data. The next advantage is optimal search storage utilization. They are important for optimizing storage utilization by arranging elements in a balanced manner. Optimal binary search trees allow for a more compact storage of information, reducing the memory requirement and improving overall efficiency in terms of storage space. Next is enhanced performance. These trees are important for enhancing the performance of search, insert, and delete operations. Their balanced structures ensures that the worst case time complexity for these operations, that is O log n, making them indispensable for applications where performance is critical. Next is statistical analysis and data representation. They play a significant role in both these fields. Optimal binary search tree are essential for representing probabilistic models and conducting analysis based on probabilistic data, thus playing a crucial role in decision-making process and data-driven applications. Next, the algorithm for constructing an optimal binary search tree is as follows. Firstly, you have to understand the optimal binary search tree construction. So, in constructing optimal binary search tree, it involves determining the arrangement of keys in a way that minimizes the total cost of searching. This algorithm is essential for efficient searching and retrieval of data in various applications, including compilers, database management systems, file organizations, etc. The algorithm evaluates the probabilities of search operations on each key and constructs a tree that minimizes the weighted average search time. This ensures that frequently accessed keys are placed closer to root, optimizing the search process for dynamic data sets. Next is dynamic programming approach. The construction of optimal binary search trees employs dynamic programming techniques to efficiently compute the optimal arrangement of keys. By breaking down the problem into some smaller subproblems and storing solutions in a table, this approach eliminates redundant calculations and optimizes the overall construction process. Through dynamic programming, the algorithm systematically evaluates all possible subtrees and recursively builds the optimal binary search tree using the computed probabilities and costs, resulting in an efficient and optimal solution. Here we're going to see the dynamic programming approach for creating binary search trees. This includes different parts. First is the subproblem identification. In the dynamic programming approach to optimal binary search trees, the first step involves identifying subproblems. This includes breaking down the large problem of constructing an optimal binary search tree into smaller, more manageable subproblems. Each subproblem represents a smaller section of the overall tree structure, and solving these subproblems will lead to the construction of the optimal binary search tree later on. Next is the bottom-up computation. So once the subproblems are identified, the next step is to perform bottom-up computation. This involves solving the subproblems in a bottom-up fashion, starting from the smallest subproblems and gradually working your way towards the larger one. The solution to the smaller subproblems are used to efficiently compute the solutions to the larger subproblems, eventually leading to the construction of the optimal binary search tree. Next is optimal substructure. This is the final step in the dynamic programming approach. This means that the solutions to the larger subproblems can be efficiently constructed from the solutions to the smaller subproblems. By leveraging this optimal substructure property, the algorithm can effectively find the optimum arrangement of keys in binary search tree, minimizing the overall search cost. Next is time complexity analysis of the algorithm. First is in worst case, the time complexity of constructing an optimal binary search tree using dynamic programming is O into the power 3, where n is the number of keys. This is due to the nested loops involved in the dynamic programming approach. Next is the average case time complexity, which is O into the power 2. This optimizes the process by storing and reusing subproblem solutions. This leads to a quadratic time complexity in the average case. Next is the best case time complexity. This occurs when the input keys are already stored, resulting in the time complexity of O of n, as the optimal binary search tree can be directly constructed without the need for dynamic programming. Next is space complexity analysis of the same algorithm. So space complexity is a crucial factor in evaluating its efficiency. It refers to the amount of memory space required by the algorithm to execute as a function of the size of the input. In context to optimal binary search trees, the space complexity is determined by the dynamic programming approach used to construct the tree. The algorithm requires a two-dimensional array to store the subproblem solutions, leading to space complexity of O n to the power 2. As the input in size increases, the space required for storing the intermediate results also grows, impacting the overall memory of the algorithm. It's essential to consider the space complexity along with time complexity to assess the algorithm's overall performance. Next is an example of constructing an optimal binary search tree. So this involves selecting a route, then recursively constructing the left and right subtrees. The key to constructing an optimal tree lies in minimizing the weighted sum of the depths of all nodes, a task achieved through dynamic programming and careful utilization of all probabilities. First, the subtree is constructed for smaller subproblems, and the results are stored, later used to calculate larger subproblems, applying the idea of optimal substructure. This allows for comprehensive approach that provides the most efficient tree. The algorithm ensures that the most frequently accessed keys are placed near the roots and optimizing the search process. As the nodes are added, the structure of the tree takes shape with the goal of minimizing the total cost of search operations. This careful construction plays a crucial role in efficient search operations, making optimal binary search trees a fundamental aspect of data organization and retrieval. Here are a few applications of optimal binary search tree. That includes database optimization. So they're widely used in database optimization. They help in efficiently organizing and querying large data sets, reducing the time complexity of operations such as search, insertion, and deletion. Next is in financial modeling. In finance, optimal binary search trees are applied in financial modeling and analysis. They facilitate quick and accurate retrieval of financial data for portfolio optimization, risk management, and investment decision making. Next, in healthcare information systems, optimal binary search trees play a crucial role in healthcare. They are utilized for efficient storage and retrieval of patient records, medical history, any clinical data contributing to streamlined healthcare operations. These are just very few applications provided here. There are many more applications of optimal binary search trees in day-to-day life. In conclusion, we can say that our exploration of binary search trees, it is very evident that this data structure plays a pivotal role in efficient searching and retrieval of data. Looking into the future, advancements in this field of data structures and algorithms will continue to refine and optimize the performance of these trees. With the increasing volume and complexity of data, there is a growing need for more sophisticated and adaptive search tree structures. Furthermore, the applications of optimal binary search tree extend beyond the traditional search operations. They're utilized in fields such as natural language processing, information retrieval, database systems. As we move forward, research innovation in this area are very likely to lead to novel applications and improvements in existing systems, enhancing their overall efficiency and scalability. Thank you. Have a great day.